Hi, my name is Scott, and I will be doing a presentation on my final project, which compares several reinforcement algorithms on a few different problems from OpenAI Gym. Here we have our reinforcement algorithms, starting with multi-arm bandit to Q-learning to SARSA, and lastly deep Q-learning. So starting off with multi-arm bandit, here we have our pseudocode that I used to implement the algorithm. The pseudocode is from a reinforcement learning textbook written by Richard S. and Andrew G. Barlow. So heading back, the policy is chosen based on epsilon greedy from whatever state we initialize at. So starting off, we have our experiments. So the first experiment was just testing the variance between each average reward for a fixed epsilon value. So here we use slot machines as the initial environment. So slot machines is an environment where we have one slot machine with multiple arms, where each arm has a different probability of giving a good payout. So here the agent will try to learn the best arm to maximize its reward values. And multi-arm bandit is specialized for this, as instead of a table of states and action, it focuses on a array of actions or action reward values. Hence, only optimize on actions regardless of whatever state you're in. So here we have our number of trials that's average per run. So here we see that in one run we have very large jaggedness as the number of runs increases and average, we have less jaggedness and more smooth lines. And here it's important that we average the number of trials, as it will produce a line that's more representative of the learner's performance instead of a high variance between each run. So moving on, we introduce a little bit of Q-learning, so in short words for now, Q-learning optimizes based on states and actions, whereas multi-arm bandit optimizes on actions. And we see that multi-arm bandit performs better because slot machines only has one state with just multiple actions for the number of arms. So hence we see that Q-learning learns slower as Q-learning has to optimize its matrix of states and actions compared to slot machines, which just optimize actions really quickly. They'll soon converge to the same value, but this shows a difference. And onto our next experiment, we perform on Frozen Lake. And the difference is that Frozen Lake has multiple states where you're traveling a matrix of values where you have to travel over a path that's all frozen and doesn't have a hole in it, essentially. Hence, we see the difference between multi-arm bandit quickly caps out because it can only considers actions regardless of state, whereas Q-learning maximizes as it considers actions with states. Hence, some actions can be better than others or worse depending on the state. So moving on to our next reinforcement learning, Q-learning. So here's our pseudocode, and in comparison, the update equation is based on the current state and action, and here our learning rate. So basically, here's our current state and action, and we basically include the maximum reward we can get from the next state from our Q table. And it also follows the epsilon greedy approach. Here, our first experiment, we experiment on different values of epsilon. So the lower the epsilon, the higher the exploration. Conversely, the higher the epsilon, the higher the exploitation. So here we see that for training, it's really beneficial to have high exploration rate, as you see that reward average quickly increases over a steep curve compared to epsilon value of 0.5, where we have explore, half exploit. Here, also implement adaptive epsilon, where we can configure epsilon to be really low, the lowest of 0.5, and it will increase over time to close to 1 as we finish the training process. And it just reinforces the fact that exploration is really important, as we still see the increases, and we can start exploring later to gain higher average rewards. So onto SARSA. So in comparison to Q-learning, SARSA is an on-policy learner, where it learns the value of the policy being carried out by the agent, including the exploration steps. So what basically this means is that it doesn't learn the maximum state or action of the next action state. It instead takes into account the exploration policy we're following it and applies this to the next state and action. Then we just update it using the reward value associated with that. And so let's start our experiments really quickly. So here we see that, as usual, multi-arm bandit performs better on slot machines, as SARSA still needs to optimize based on state and actions. Next, we have our Frozen Lake comparison between Q-learning and SARSA. Here we see that actually Q-learning performs way better than SARSA, and the reason this is because SARSA results in a policy that is near optimal, basically a local maximum, whereas Q-learning results in a policy that's always the best. However, and we can see this follows the similar trend as shown before in comparison to Q-learning, with lower epsilon and higher epsilons and adaptives. Okay, and here I want to show reasons why we might consider SARSA. So cliff walking. So consider we have to find a path around the cliff. Here, Q-learning will always find the most optimal path, but it's also the most dangerous path. Hence, SARSA can be considered if say you're considering training a robot that's in real life. You might want to consider a path that's more safe to reduce the damage to equipment. Hence, that's usually when SARSA would be considered, as penalties affect SARSA way more than Q-learning. And lastly, we have deep Q-learning, where we highlight the effectiveness of introducing neural networks to training with Q-learning, as neural networks are able to train on a wide variety of weights and features. Here I use a simple neural network that has a input layer of the amount of observation, basically the amount of states. And here we have our hidden layers which the neural network will produce an output, and output is the size of the action space. And basically, the action we take is the maximum index of the values it returns in its tensor. So starting off with our experiments, since neural networks take a while to train, we just did a few experiments, and here we compare Q-learning to deep Q-learning, and we see that deep Q-learning is able to learn higher average rewards compared to Q-learning, as it's able to consider many weights in comparison to just a tabular table. And here's a simulation of a playthrough for the agents. And yeah, that's pretty much my project.